So we are approaching the end of our lecture series for Stat 331. So one of the last things I want to do is to give you a brief introduction to what we have after 331. Okay, so I'm just going to call today's lecture a brief introduction to what we call generalized linear models. If some of you have the interest to take one of our follow-up courses, it's on GLMs. Okay, so I'll call this Beyond 331, and this will be a brief introduction to generalized linear models. Okay, so we abbreviate that as GLMs. Okay, so generalized suggests that the multiple linear regression that we've been focusing on this term together is a special case of generalized linear models. Okay, and so we have the ingredients are as follows, and we're quite familiar with this framework. We have a vector of responses. Okay, so let's put that as a vector, which are independents. Okay, and then we have predictors. For explanatory variables in the usual framework, let's write them as vectors. P of these predictors, x1 up to xp. Okay, so what is the generalized linear model framework? Okay, so there's three ingredients to a GLM, and then I'll explain why multiple linear regression is a special case of this. Okay, so three ingredients of a GLM. Okay, so the first piece is that we have a random component. Okay, and so the random variables in the GLM are these responses. Okay, so just like in multiple linear regression, we treat our responses as random and our predictors as fixed. So that will still be the case here. Okay, so in generally, we say the response, so the yi, response yi is a random variable. Okay, so we treat the response as a random variable. Okay, and so random variables have probability distributions. Okay, so with a distribution. Okay, and so the generalization here is that we treat yi can come from a number of different probability distributions. In particular, the technical term is in GLMs, the yi's come from an exponential family. So commonly used distributions in the exponential family include normal, which we're very familiar with, and it also has things like the binomial and the Poisson distributions. Okay, so with a distribution that is a member of an exponential family. Okay, so we won't go into the details here, but we will give some examples of distributions that are famous and are part of the exponential family. So common examples of exponential families include the normal distribution, which we've used a lot this term, binomial, and also Poisson. Okay, so those are all within the broad class of distributions that fall within an exponential family. Okay, so that's first component of a GLM. Okay, and then second one is we have a deterministic part, or systematic, otherwise known as a systematic component. Okay, and so this is what we're very familiar with here. Is typically a linear predictor in terms of the available explanatory variables. Okay, so this is typically a linear predictor based on the variables we have. Okay, so yi you would have xi1 up to xip. Okay, and so for development, let's give this a notation. So let's denote. Let's use a different letter. Let's use the eta. So let's define eta sub I to be exactly that linear predictor. So as we've seen, beta 0 plus and then the usual regression coefficients times the predictor. So this is the linear predictor that we've spent much of our term studying. Okay, so beta p xip. Okay, and so the reason for defining an additional notation will be clear in just a second, because the generalization is this doesn't have to be, we don't have to put just the expectation of yi, for instance. Okay, so this is the usual linear predictor, the form of it that we've seen using regression coefficients and then the p predictors. Okay, so the reason for introducing a new notation here is now we're going to link, the third component is to link these two together. So we're going to link together the random and the systematic via what we call a link function. Okay, so all this is a function, let's call it g, okay, which defines the relationship between aspects of the random and the systematic. Okay, so that defines the relationship between. Okay, so from the random components, we're going to link the expectation of the random variable. Okay, so because yi is treated as random, we'll have an expectation. So this is so the link is between this expectation and this systematic component. Okay, so that's why I defined eta I here. Okay, so remember that this e of yi comes from the random part. And then this comes from the systematic part. Okay, and so in other words, we're saying this function g links these two. So specifically, I can express it this way. So eta I. So this systematic part can be written as some function of the expectation of the random variable. Okay, so those are the ingredients of what we call a GLM. Now, I want to give you two examples of this framework. And the first is simply to relate this framework to what we've been doing already in multiple linear regression. So the first example is to see why multiple linear regression is a special case of this framework. So let's look at what these three components are in the case that we're most familiar with. Okay, so yeah, so our first example is simply multiple linear regression. Okay, so keeping these things in mind, well, what's our multiple linear regression model? Well, we say yi, which is the random variable, is the regression part, so beta 0, beta 1, x, y1, beta p, is ip plus epsilon. And we have assumed that epsilon is IID, normal, all with the same variance, sigma squared. Okay, and so in multiple linear regression, well, the random component. Okay, so what's the family of the distribution for the responses? Well, we've been assuming it's normal. Okay, so let's write these things up. So in multiple linear regression, the random component is normal. Yi has a normal distribution. Okay, so that's a special case of the exponential family, and multiple linear regression is a special case of GLM. Okay, so what are these other components? Okay, so we have the systematic is this linear part. So how is the expectation related to eta? Okay, so we have yi is normal, and the expectation of y, according to this framework, is, well, the expectation of y, because of how we define epsilon, is simply this this regression part, which I've denoted here eta I. Okay, and so therefore we see what's the function g that links eta and e of y. Well, g is simply the identity, right? G of x equals x is the function that provides the connection in multiple linear regression. Okay, and so the link is that g, in other words, g of e of yi is simply e of yi. Okay, so that's the identity function. Okay, so we see that multiple linear regression falls within this framework. Eta here is actually just the mean of the regression when in what we've studied in multiple linear regression. Okay, so that's first example. Second example is so I do want to introduce you briefly to logistic regression as an example of GLM. So as mentioned, GLMs are the topic of its own course. It's 431 here at UW. And so I just want to give you a brief overview of an example of a GLM beyond multiple regression. Okay, so our second example is a brief introduction to logistic regression. Okay, so the framework for logistic regression is where we have where the response yi is binary. Okay, so it can be used when the response yi is binary. Okay, so I want to distinguish this from something we have looked at. Like we have used categorical predictors in multiple linear regression. Okay, so when some of the x's are binary or they have several categories, we learn how to use them in our regression model. But remember that in all of the examples we've seen so far, the response, we've treated that as a continuous variable. Okay, so in particular, we treat the response as a real number. Okay, its average value is the regression part, and then plus some normally distributed noise. Okay, so here in logistic regression, it is not easily covered by our usual multiple linear regression framework, because normal errors, of course, don't make sense when the response is just 1 or 0. Okay, so therefore, probably one of the first GLMs that we'll see is to cover this case of how to model a binary response. Okay, and so in other words, yi is either 1 or 0. Okay, and so this could mean a number of things, right? So 1 could mean a success, 0 could be a failure. Okay, so that reminds us of the binomial distribution. Okay, we could represent other things, right? So 1 could be on, 0 could be off. 1 could be yes, 0 could be no. 1 could be a goose, and then 0 could be, not a goose, so non-goose. Okay, so anything that we can represent in binary, when there's only two classes, then we can view it in terms of a logistic regression and build a logistic regression model to understand the relationship between yi, which is binary, and the predictors that we have. Okay, so how does this fit in the GLM framework? Okay, so what's the random component? Okay, so random component is looking at the response. Okay, so we're treating yi as a random variable, so in other words, it will have a probability of being 1 and a probability of being 0. Okay, so we need a probability. So in this case, there's only 2 outcomes, so we can just write it as a discrete probability distribution. So we're going to have a probability that the ith observation is 1. So we need to define a probability for that. Let's call that pi sub I. Okay, and that defines a probability distribution. Okay, so in other words, the family that this distribution is part of is the binomial, right? So yi is a binomial. Okay, so here there's just one trial, so it's either 1 or 0. One trial, and then probability of success is this term I defined here, pi I. Okay, so the exponential family here is binomial. Okay, it's a probability pi I, that's 1, and then otherwise it is 0. Okay, so that's the random part. Okay, so where does the predictors come in? Well, now we have to think of the predictors as intuitively impacting the probability that y is 1 or 0. Okay, so for certain values of predictors, y might be more likely to be 1, whereas for other predictors, y might be more likely to be 0. And so the idea now is to use our predictors, so use all the x variables and the regression coefficients beta to explain the relationship between these probabilities and the predictors. Okay, so the GLM provides a framework for doing that. Okay, and so in the logistic regression, we use a specific link function, and I'll explain that next. Okay, so the link function for logistic regression is the logit, known as the logit transform. We'll write it down first, and then I'll explain it. Okay, so what it does is we're taking these pi i's, and we're taking the log of them, applied to pi I over 1 minus pi I, and we're setting that equal to the linear predictor. So let me write that again. So I1. Okay, so in the GLM framework, I call this whole thing as simply eta I. This should be not is sets. Okay. All right. So there's a bunch of things to explain here. So let me try to do that in a systematic way. Okay, so what's going on here, and why do we have this model structure? Okay, so the first thing to note is, okay, so notes about this. Note the following. Okay, so what is pi I here? So if you have if yi has this distribution, okay, so it's 1 with probability pi I and 0 with probability 1 minus pi I. So what is the expectation of yi? Well, we simply use our rules for this simple PMF. Okay, so expectation yi is 1 times the probability that yi is 1, so 1 times pi I, and then plus the value 0 for the probability that it is 0, 1 minus pi I. And so pi I is indeed E of yi. Okay, so this is the expectation. So this is the thing that we relate in the GLM framework to the predictors. Okay, and so the function g, so logistic regression takes the function g and relates it to the linear predictors by taking log of pi I over 1 minus pi I. Okay, so that's the form of the link function. Okay, so as I mentioned, this is called the logit link. Okay, so why does that? Okay, so that's first point. So second point is, well, what interpretation does this form have? Okay, so I want to mention odds, because this is where this is coming from. Okay, so let's say A is an event in the probability sense. Then the odds of event A is defined as the probability that it occurs over the probability that it doesn't occur. Okay, so that's the technical usage of odds. Sometimes we use it. Sometimes we just use it colloquially to refer to probability and stuff. But this is the actual definition of odds. So if I'm rolling a fair 6-sided die, the odds that I get a 1, well, they're 1 to 5, right? the ratio, the probabilities of it happening to not happening is 1 to 5. So that's called the odds. Okay, so in that sense, so keeping this fact in mind, then the expression pi I over 1 minus pi I, well, what is that interpretation? Well, it falls into this framework. The event here is whether yi is 1 or not. Okay, so this expression is the odds that yi equals 1. And if I take the log of it, okay, when I say log here, we're referring to the natural log, base e. So then the log pi I over 1 minus pi I is the log, call that the log odds, that yi is 1. Okay, so that's how we can interpret this particular function, log of pi over 1 minus pi I. Okay, so that's those are a couple things to note. Now, next is, well, what does this transformation do to pi I? And okay, so that's one point, is the expectation. Second is odds, and it's in the interpretation of this. And the third point is, well, what does this actually do to the probabilities? Okay, so since we're setting the deterministic part, so remember this is the entire eta I is the entire linear predictor, and we're setting that equal to log pi I over 1 minus pi I. So we can invert this function and figure out, well, how is the probability that the ith observation is 1 related to the linear part? Okay, so let's solve this for pi I. Okay, inverting this function. Okay, so first let's get rid of the log. So we'll exponentiate both sides. So this is e to the entire linear predictor. This is pi I over 1 minus pi I, and then from here we solve for pi I, and after simplifying we get pi I equals e to the eta I over 1 plus e to the eta I. Okay, and so to get some intuition, well, let's draw a graph of this function. Okay, so let's do that over here. Okay, so let's plot y equals e to the x over 1 plus e to the x. Okay, first thing we see here is that this function is going to be between 0 and 1. Okay, and that makes sense because pi I is a probability that yi equals 1, so that's going to be bounded below by 0 and above by 1. Okay, in particular, we can plot this. So when x is 0. Okay, so when x is 0, you have e to 0 over 1 plus e to 0, so it's 1 over 1 plus 1. So it's going to be 0.5. Okay, and then as you take x getting larger and going to infinity, we notice that the limit of this is 1. Okay, and then likewise when we go in the other direction, take the limit x goes to minus infinity, then the limit on the left side is 0. Okay, so if we put that together, then this graph looks something like this. Okay, and this is 1, and this is 0. Okay, so these are those are the limits of this function. Okay, so what we see then is, notice that pi I, as we know, is a probability. So this is bounded by by 0 to 1. And what this transformation does, and log pi I over 1 minus pi I, can take any real number, while okay, so since we're using the regression to predict this quantity, okay, so the linear regression part can take any real number, which is the framework that we're used to in doing multiple linear regression. Based on the coefficients, we get a real number for this log odds quantity, and then we can plug this into invert this function to spit out the actual probability that y is 1. And we know by definition of this function that we're going to end up with a valid probability that lies between 0 and 1. Okay, so that's what this this logistic function does, and therefore it helps us model the probabilities of binary events. Okay, so the final couple notes I want to make is interpreting the coefficients. Okay, so do that here. Okay, so alright, so let me write it out so it's clear. So since log pi I over 1 minus pi I is modeled to be this linear predictor, xi1 px by p, and then we also know the probability that yi equals 1 is equal to pi I. Okay, so that summarizes the model setup that we have. Okay, so in this context, then we can interpret the coefficients. Okay, so therefore, then beta j. Okay, so using our usual interpretation, so if I change x, a variable in here by 1 unit, then the corresponding change on the left hand side, well, it's beta j. Right? So what is the left hand side? Well, it's the log odds. Okay, so we can interpret these coefficients beta j as the corresponding change in the log odds. Okay, so beta j is the expected change in the log odds of the event that y equals 1. Okay, and then the rest of the interpretation is the same. Okay, so for a unit increase, in the variable in xj. Okay, again holding other variables constant. Okay, so our usual interpretations for the regression coefficients applies directly to the log odds, because the part of the model that is linear, and what we're familiar with is this linear part is related to the log odds of y being 1. Okay, so that has the usual interpretation. Now, if we go from log odds to odds, then all we have to do is exponentiate. Okay, so that's the next part I want to mention. So if we want to interpret it in terms of the in terms of the odds as opposed to the log odds, then we want it to exponentiate. So, and okay, so if I take e on, I raise e to the power on both sides, I cancel out the log, and over here I'm going to have e to the beta 0 plus in this linear part. Okay, so now if you look at this part, so on the scale of the odds themselves, so if I now increase one of these predictors by 1 unit, then the corresponding change is now a multiplicative change because this is exponential, and so the change will be e to that coefficient. Okay, so then e to the beta j is the expected multiplicative change in the odds. Okay, since we've exponentiated, so this is multiplicative change in odds is the same as change in the additive change in the log odds. Okay, so this is the key difference. Once we exponentiate, we're on the multiplicative scale because of this expression here. So e to the beta j is the expected multiplicative change. So if you add 1 unit to one of the x's, then the odds changes by a multiplicative factor of e to the beta j. Okay, so finish the sentence in odds of y being 1 for a unit increase in xj, again holding other variables constant. Okay, so that covers the basic idea. So the linear expression is related to the log odds. Okay, so therefore they are not the probabilities themselves are not going to be linearly related to the predictors, because the predictors are linear in the log odds, and then we have to do a couple of transformations in order to get back our actual probabilities for yi being 1. Okay, so I want to illustrate this with just a quick numerical example on the board, so you can see this stuff in action. So I'll leave that picture up here, so you can see the relationship between the predictors and the probability is not linear. Okay, because it's according to this logistic function. Okay, so higher values of eta I will give us a higher probability that response will be 1, but it's not linearly so. So let's give an example, and just before I do that, let me just make one final note. So how do we fit the model? Okay, so the model is generally fitted using likelihood methods. Okay, so the model is fit using maximum likelihood. Okay, we'll do the MLEs. And in R, so you don't need to know that for this course, but just as a heads up, we've used. So remember when in the models we fit for regression, we use LM, right? So we've just used LM many times, and the corresponding one to fit generalized linear models is not surprisingly GLM. Okay, so this is done using GLM function in R. Okay, and so just as a heads up, if you do take stat 431 as a follow-up to this, then you'll be doing a lot of analyses using GLM. Okay, so that was the last note I wanted to give you. Okay, so a numerical example. So last time I mentioned one of our a data set that involved the string quartets of Haydn and Mozart, and trying to so where that data set came from was in some research that I did with one of my former students, and we were trying to classify. So we were looking at the notes on the music score, so the quartets. Like, are there certain features of the music that make that piece of music more Haydn-like as opposed to more Mozart-like. Okay, so Haydn and Mozart were two very famous composers in the 1700s, and so this problem has fascinated musical scholars for quite a long time in terms of, well, what makes a piece more Mozart-like as opposed to Haydn-like. So they were contemporaries of each other, and often wrote to similar kinds of audiences, and they both wrote many string quartets. Okay, so those are pieces of music with four voices. So there's two violins. There's a violin 1, violin 2, and then a viola and a cello. So that was a very common form of chamber music, and many of their quartets are still quite popular today. So in that paper, what we tried to do was to detect several features based on the music scores that actually help distinguish these two composers from each other. And so a natural base model to work with was logistic regression, because that helps us. In this case, we have two classes, Haydn and Mozart, and we want to distinguish which of these two binary classes a piece of music is most likely to be. Okay, so I'm going to just give you a quick, so here's a practical example, is music analysis, where yi is either 1 or 0. Okay, so in this case, we're going to say 1 is the piece is by Haydn, and 0 is by Mozart. Okay, and so for string quartet classification. Okay, so of course there's quite a bit of work involved in building this model, and I just want to give you a snapshot just to illustrate how logistic regression works in practice. Okay, and so suppose we fit the model log pi I over 1 minus pi I. So I'll just give you an excerpt of the model. Let's say we just take a couple of predictors. So in practice, we actually found 7 or so important predictors, but just for the sake of illustration, I'll just write down a couple. Just so we can illustrate the model. Okay, so let's pretend there's just two predictors, x1 and x2, and those are going to be related using this formula. So these are going to be linearly related to the log odds of whether that piece was written by Haydn versus Mozart. Okay, so let's just say okay, so this is just for illustration. The actual model we had 7 predictors. Okay, so suppose we have fit the model, so we have a bunch of training data for this classification task, and suppose we have fit the model and we have estimates for these coefficients. Okay, so as mentioned, we will do that using MLEs. So we used something similar to the GLM function in R, and suppose we have estimated these. So from training data, okay, so in other words, a bunch of observations with yi's known and predictors given. Okay, so suppose we have these estimates. Okay, so beta 0 was minus 1.2. Beta 1 hat was minus 15.47, and then beta 2 estimate was 16.71. Training data, MLEs are following values. Okay, so for the three coefficients. Okay, so in order to interpret, I'm gonna explain what these predictors are. So x1 for your purposes. So the first predictor in the model, it was the standard deviation of note durations in the first violin part. Okay, so this was a statistic that we computed from the music scores and determined to be an important predictor for being able to distinguish Haydn and Mozart. So one of the seven. Okay, and then just for illustration, here's one more. X2 we found as an important predictor. It's the proportion of descending pairwise intervals. So, I mean, this is a technical music term, but imagine the intervals are the distances between notes, and then each pair of intervals. So what fraction of them are descending as opposed to ascending intervals? Okay, and it turns out this is also a useful predictor, and this is also calculated on the first violin. In first violin. Okay, so we had several other predictors, but just to illustrate this logistic regression framework and to give you do some calculations with you to show how it works, I'm just going to leave it at two predictors. Okay, there's a comment. Okay, so we have a Beethoven fan in chat. Beethoven was considered more of a probably less similar to some of the other contemporaries. Beethoven was also writing a little bit later, so it has a few more touches, I guess, of more romanticism and other more experimental elements in his music. So I would say slightly more stylistic differences compared to Haydn and Mozart. So if we were to plot like a pairwise distance matrix between the three of them, Beethoven would be quite a bit more different. Okay, so let's interpret this model. Okay, so suppose we have these two predictors. So I just want to show you how this works. Okay, so 1 is Haydn, 0 is Mozart. Okay, wish I had a bigger board, but let me make some room, and then let's do a few calculations to wrap this up. Okay, so first thing I want to note here is, okay, well, what is the effect of these signs? Okay, so beta 1 hat is negative. Okay, so let me just add here. Remember, yi 1 is Haydn and 0 is Mozart. Okay, so this coefficient is negative. Okay, so therefore, when x1 is higher, okay, so this linear part is going to decrease. Okay, so in other words, the log odds are going to decrease with higher values of x1. So therefore, higher values of x1 are more likely to be Mozart. Okay, so the probability will decrease. And then in contrast, higher values of x2, the sign is positive. So higher x2 will have a higher probability of being Haydn. Okay. So the question is there no love for the original gangster J.S. Bach? So actually, interestingly, Bach has been subject to a lot of music analysis as well, because he also wrote at a time when in the Baroque period when again there were other stylistically similar composers writing, and I think one thing was pretty interesting is in some studies that we read. People had a lot higher classification accuracy rates trying to classify different Baroque composers than compared to these two classical composers. So in this case, we were only able to achieve about a little higher than 80% classification accuracy. So if you're just randomly guessing, you get 50%. So our model got up to about 83, 84%. Apparently, distinguishing Bach from some other Baroque composers is actually a little bit easier, and some previous papers reported over 90% classification accuracies. Another interesting direction, since we're on the topic of Bach, is so he wrote a number of chorals. So they're also four-part, but in terms of four-part voice harmony, and so kind of a complementary direction in music research is well based on a bunch of training data of Bach chorals, can we automatically like simulate Bach? So can I use a machine? So after training the machine, can I write Bach-like music? So that's another interesting application of so-called AI to what we call music generation. Okay, but I digress a little bit. Let's finish up this discussion here. Okay, I don't think I need this plot anymore because I've already explained how the relationship is linear in the log odds, but it's non-linear in the probabilities. So I'm gonna get rid of this graph so I can give you a little more information about these predictors here. Okay, so standard deviation, no duration. So I just want to give you a rough range of these values, range of predictor values. Okay, so this value in the data set is ranged from about 0.05 to 0.35, and then for x2, the range of values in the data set was from about 0.2 to 0.5. Okay, so all right, so let me first write down what I was saying verbally just a few minutes ago. So because of this is negative sign, and then 1 is Haydn, 0 is Mozart. So in general, we can say that higher values of x1 in this case are associated with are more likely to be Mozart. Okay, because of this negative sign, and similarly, higher values of x2 are associated with a higher probability of being Haydn. Okay. Okay, so just to illustrate, let's try plugging in a couple values. Okay, so I'm going to use this formula, but I need a little more room, so I'm right, give us a few values. Okay, so specifically, what is the relationship then, given these estimates? Okay, so suppose we have some values, x1 and x2. Okay, so let's suppose we have a few different values of x1. Let's say 0.05 or more on the lower end, and say we have 0.2, which is closer to the middle of the range of x1, and then we have some high values of x1. And just for sake of argument, let's fix x2 at somewhere in the middle. Let's say 0.4. Okay, so we know that, in other words, in this interpretation, right, since we're holding x2 fixed, if x1 is larger, that suggests that among these three sets of predictors, well, this one is the most likely to be Mozart. Okay, so as you go this way, okay, in terms of x1, more higher estimated probability, okay, based on the beta hat. Probability is Mozart, since beta 1 hat is negative. Okay, and I'm just going to hold x2 fixed for our purposes. Okay, so let's do a calculation. So if this is the value of x1, this is the value of x2. My estimated log odds of y being 1. Okay, so that's the linear part. So so this is the eta I. Okay, so let's plug in the linear part. So you have the intercept. So it's minus 1.12. 15.47 times 0.05 and plus 16.71 times 0.4. Okay, so that's the estimated log odds based on the logistic regression model. So that's this value, and then from there I need to convert it. So the estimate of II. Okay, so let's call this thing. Okay, so what is this number? Let me just work it out. Since I need this number, minus 2 minus 15.47 times. Okay, so this is 4.79. Okay, so how do we use this number 4.79? So this is, you can call this like the estimate of eta for this for these values. Okay, so just colloquially just call it eta I hat. Okay, just for sake of argument. And so to convert this to the probability, estimated probability, then I need to do e to the eta I hat, okay, 1 over plus e to the eta I hat. So that will convert this linear part into a corresponding probability. Okay, so eta I here is pretty high, so it's like e to the 5 over 1 plus e to the 5. Okay, so that's a pretty, e to the 5 is pretty large. So you can see this is going to translate to a very high probability of this piece being hidden. Okay, so what does this come out to be? This is like 0.992. Okay, so in other words, based on our fitted model, okay, so we use these numbers now. So this is the estimated probability that the piece was composed by Haydn for x1 if x1 was 0.05 and x2 was 0.4. Okay, and so just to illustrate, we can do the same calculations for these two values, just to see how the probabilities change. Okay, so as mentioned, holding x2 fixed, by increasing x1, I'm going to be subtracting a larger number in this part. Okay, so I'm plugging in 0.2 and 0.35, so this eta I hat would be smaller for these larger values of x1. Okay, so you can check later, you can do these calculations. Okay, so for these guys, okay, so this one, the estimate comes out to be 0.922, and then meanwhile, if you further increase x1 and do the similar calculation, the final probability we get is 0.537. Okay, so as we explained, we have a negative sign on beta 1 hat, so increasing x1 is going to ultimately cause the probabilities to drop. Okay, so these are the three sets of probabilities. So from 99% increase x1 bit drops to 92%, and increase x1 by the same amount. So you added plus 1.5 and plus 0.15, and then the second time it actually drops the probability a lot. Okay, and so this is what we mean by the actual probabilities are not linear in the predictors. The log odds are linear in the predictors. Okay, but nonetheless, the coefficients tell us the direction of how the probabilities are going to move. Okay, so that's how we can use a fitted logistic regression model, just to illustrate that the goal here is to give an estimated probability. Now, in practice, so if I'm trying to predict for a piece of music I haven't seen and I get a probability of 0.99 that is Haydn, then most likely, if I had to guess, I would say, okay, well, I think this piece is pretty likely to be Haydn. So if I need to convert that to an actual guess, then I would probably, in most cases, I would guess the more likely class. Okay, so in this case, I'm pretty sure it's Haydn. So now when we get to this case, 0.537, it's still, according to the model, more likely to be Haydn than Mozart, but here we're much less sure. We're looking at like a 54% probability. Okay, so what we're estimating is the probabilities of that piece being Mozart versus Haydn. So we can convert these probabilities into actual predictions, 1 or 0. Okay, so that's the gist of how the logistic regression model works. So let's just close by making a comment about beta 1. So let's just write out the interpretation. So okay, so for a unit increase in the standard deviation of notes duration in the first violin, the estimated change, expected change in the log odds of the piece being Haydn is minus 15.47. Okay, so it's linear. It's linear in the log odds, and the actual effects on the probabilities are nonlinear, although we can tell the direction of the effect. Okay, so that's all I wanted to say about GLM. So this is really just a brief overview of some of the techniques and models that gives you a preview of our GLM course, which is that 431. Okay, so just before I close, are there any questions? There's a question, do I teach any music history courses? No, that's not my specialty, but as you may have inferred, given the data points that I've given you this term, that I am quite interested in music, and so it's kind of fun to be able to apply statistics to areas that we are interested in. So that's why this was a pretty neat project that I gave you a bit of a preview here of taking statistical models and trying to analyze music and to use quantitative methods to we enrich our understanding of music by applying quantitative analysis to complement all the qualitative analysis that music scholars have written over the centuries. So that to me is a pretty cool in terms of being able to apply data science to these areas. Okay, so with that then, we will have our final stream for the course on Wednesday. And then after that, you'll simply have time off from lectures so that you can work on your final projects. All right, so we'll see you online one last time on Wednesday.